Okay, dear students, this is another okay. This is another lecture on linear DAEs with variable coefficients. Last week we have learned in a few examples why this is so difficult, and then we have talked about equivalences. There was this global equivalence, and there we had, for example, e tilde of t is p of t, e of t, q of t, also of t. And then we had this local equivalence where we had again e of just the e as p eq as we knew it before, but there was this a now being p aq minus p e r r. Yeah, and this came from this a tilde that we had here, where there was this q dot involved. I hope you all remember that. Today we will first introduce some more notation. Then with that we will derive a local canonical form, and then there will be an example. So first I will try to explain this local canonical form a bit, that you can more or less see as an example, and then we will take the circuit example and look for what this looks like in this canonical form. Not in the canonical form, but what are the spaces that make up this canonical form. Okay, but first we have to start with some notation. And the first notation will be actually some to make life easier, we will just say that the matrix spans the space V. Well, basically, if the columns of span this V. Okay, actually we cannot say that a matrix spans a vector space. We can say that, but that's not what we meant. Single matrix will span only a one-dimensional vector space, but if we if M was these columns v1, v2, v3, then we say, well, then we can identify this with the space, the span of v1, v2, v3. Okay, that's how we say that this matrix spans the vector space. And also we say that this is a basis of the space V if the columns of M form a basis of. Okay, so we say matrix M spans the space V if the columns here are the columns, if they span the space, and this will make life much easier. Another notation that I'm gonna take another. What horrible color is this? Okay, then another notation that we want to use is we take a matrix T. So T is say an R n times K matrix. Then we say T dash is a matrix in R to the n minus K, so that if we put them both together in one matrix T and T, so they have the same number of rows, so we can put them next to each other. And this in particular is R to the n matrix, and this T dash should be such that that this matrix is invertible. this of course needs that here these vectors has full rank. So all vectors out of this matrix, they should be full rank, and then we can find like the other n minus k vectors that are also linearly independent in R or C, of course, such that this matrix is invertible. This will then be also a basis of this space with this notation that we had up here. Then we will use this V to the H, which is the Hermitian transpose. And this is basically transpose plus complex conjugate. Well, in all examples we will have real matrices. Let's have this little example. Say A was this matrix, 1 plus 2i, 2 minus 5i. Then we would have that AH as first of all the transpose. So this will be a matrix that looks like this. And then the complex conjugate is taking the minus out of these. 2 plus 5i. So this will be the complex conjugate. And for real matrices, where we don't have this and don't have this, and don't have this, don't have this. So real matrices, AH is AH is same as just the transpose, because there's no need to take the complex conjugate. Then we will need the kernel of A is that V such that AV is 0. Then the range of A is this is basically the range of A is what the span that M spans. So that's range of A. Shall I write it down there? Okay, that this is the V in Rn such there exists a Y in Rm such that V is a Y. So that's, so to say, all vectors that we can construct with the columns of the A. Corange is the corange of A is the same as the kernel AH, and co-kernel kernel of H is the kernel is the range of AH. Okay, so now you have all together. I hope that in the script there's also this co-range, range, and so on explained. Co-kernel. Okay, and with that we can now consider this theory that will define this canonical form under local equivalences. So for this theory we take E and A to be m times n matrices, m times n, so no need to be square, but fixed matrices, so no functions. Then of course we can consider the kernel of this E matrix. We can also consider the corange of E, which is the kernel of EH. We can then, we say that this is T is the basis of this kernel. Then of course we can complete this. And in this case, this completion can even be the co-kernel of that. So the range of EH. That one can show that the co-kernel and the kernel, that they complete each other. So that this can be the t and this can be the t dash. And then we have the z, we have the t, and of course we have the a. So we can also look up what is the co-range of this zh, at. And if we have these matrices t, z, th, and v, then we can define the quantities r, which is the rank of E. We can define the rank of this matrix here. This will be the A. Then we can also define the rank of this matrix here, ZH, AT dash, and with this V VH multiplied, this will be the S. And then based on these RAS, we can also define the D, which is the R minus S, the U like this, and the M like that. So this will be the algebraic part. That's why we have the A for that, algebraic part. I will motivate this later. This will S like in strangeness. D like in differential. R like in rank. U like in undetermined, and V like in vanishing. This will be vanishing equations. Okay, and so what the theorem says is that these R, A, S, D, U, and V are invariant under local equivalent transformations. So EA, we can transform EA and then we will always get R, A, S, D, U, V to be the same numbers. And what the theorem also says is that the E and the A can be locally made similar to this form. Here we have this IS, which is this S here, for example. The ID, which is this D here. So the E matrix will look like this with this block here, IS and ID. And the A matrix will be also reduced a lot. And here we see this IS again. So here and here. And here's this IA, and this is this algebraic part. Well, and if you look at that, then you'll see already that here, if this is so if you look at this like EX dot as AX, then for example here you will see that you only have this A acting on the X. And for the ID, here you see that's only the E acting on this. That's why this is the differential part. But I will have more examples on that. Okay, so theorem says, let me say this once more. For E and A, we can construct these matrices. From that, we can derive these quantities, R, A, S, D, U, V. And the theorem says that these quantities are invariant under local equivalence transformations. And in particular, through local equivalence transformations, we can turn EA into this form. And the proof is very technical, and you can find this in the book by Kunkel-Mehrmann. There it's theorem 3.7. But I want to rather talk about what are these quantities. Basically A, R, well R not so important, A, D, and S. So algebraic, differential, and strange parts. Well, let me motivate this like this. So consider again this EX dot is AX plus F. Here E and A are constant matrices, but actually for what follows, it wouldn't matter if this is E of t and A of t. Then of course you will get the kernel T of t, you will get this co-range Z of t. So this will depend on T2, but doesn't matter for what we consider now. Well, now let's say the T is the kernel of E, and then we can complement this. So here this was this T, and then we can make this the full matrix, and then that's why we can did I want to do something here? No. Why is this down here? Well, anyways, this means that we can this makes an invertible matrix, so we can consider like the transformed x is t dash y of t. So this is a state transformation. We can just consider our actual state to be t times t. So this matrix t, this matrix made of t and t dash times some other variable. So this is the state transformation. And then we have the co-range of E, which is the kernel, so Z kernel of EH, and this in particularly means that ZH E is 0, because EH Z is 0. This is what is meant by the kernel, and, well, and then we can take the transpose of here to get that ZHE is just a 0. Okay, and now if we like do the state transformation, like x of t is this t dash matrix times y of t, then we can, let me show you this in more detail. So we have here the t, we have this matrix t dash, and this is multiplied by the y actually, but we can also of course split the y into the y and the y dash of t, and this is then, if we multiply this out, ty of t plus t dash y dash of t. Okay. All right. What does this mean? This in particular means that, so we have the x written like this and in this form, and this in particular means then if we consider E x dot, that is the same as E t, okay, make this in all detail, ty t dash ty, this is the same as E t y plus E t dash y dash dot dot dot. Okay, and since t is the kernel of the E, this is 0. This is just 0 because t is the kernel. So we end up with this, and here we have on this side, this equal side, that we have, well, this will give us a t y plus a t dash y dash plus f. So we are then left with this equation. What we can see here already is that these y dash variables, that are those that will be differentiated. Okay, and then what else we had? We had z to be the co-range of E. So if we multiply now by ZH, multiply to that, and this will, okay, wait, what did I want to do with that? Okay, this will cancel this out as well. Then we will have here the 0 as the same. Okay, no, I know what I wanted to tell you. Oh, actually I said it. So here, these are the variables that are differentiated. The y dash, that are the variables that are differentiated. Now we apply the ZH to this, then we get a 0 on the left hand side, and we will get ZH a t y plus ZH a t dash y dash plus f of t plus ZH f t. So what I want to do here, so we can put this on this side here, and then we arrive at ZH A T y is minus, that's because it's on the other side, ZH A T dash y dash plus ZH f. And now what we have for this y dash, for these y variables, these are variables that are not differentiated because this here is 0, so the y will never get differentiated, and they are defined through this relation, which is a purely algebraic equation. So here y not differentiated and defined through algebraic equation. And that's why it makes so much sense to call this here the algebraic part. That is what defines the algebraic part, is that ZHAT. And let us go back to the theorem. So A is ZHAT. If this is full rank, then that's like all of that. If this is not full rank, then there will be some unknown, some undefined or vanishing equations in there, but the rank of that will define the algebraic part of this equation. Okay, that's the algebraic part. Now we can see what do I miss something here? Yeah, I know what I was missing. Okay, so now we can look at the co-range of ZHAT, which in particular means that we will have VH ZHAT is 0. We apply this here, then this will be cancelled here, and so this is not right here. No, anyways, I'm on the wrong layer. Oh no. Okay. Too bad. No, anyway, that's okay. So this was not right here. Here I wanted to have still I wanted to have, so here we have t and t dash times the y. So this is where we started in here, ZHAT with all this. And now we apply the VH to that from this side. Then what will cancel out is this part here. So this will give us 0 is VH ZH A. The t part cancels because of this here. And we will only stay with the VH the dash part times the y dash plus what stays with the right hand side, VH ZH F. And this part now is interesting because I hope you all remember these were those variables that are differentiated. If we go back here, so here, these are the variables that are differentiated, meaning for those we now have a differential equation, but we also have like this poorly algebraic equation. Now this is really a poorly algebraic equation that says these variables are proportional to this right hand side without any differentiation involved. So what we have here, differential variable equated algebraically, and both that together, this is strange, as they call it. Strange. And in fact, that's also why this part here, this defines the strangeness. And of course, this sounds strange in the German sense of, well, fremd, or well, strange, but it basically means skewness, and skewness means sheaf in German. So something is not straight or not even. They're somehow skewed. Okay, so this makes a lot of sense to name this the strangeness. And if we look back into the canonical form, that's also what we see here. So here we have this differential part, like this part will be E dot is something equal to a right hand side. But here we also have this part saying that these variables are also algebraically related to the right hand side. Okay, and since we have both here, like algebraic and differential relations for that, this is what is called the strangeness. And then, we can have a final look at what is the differential part. So D is R minus S. This is D is the rank of, R is the rank of the E. So this names all this together. This is how many variables are differentiated. But then we have to subtract the S, which are those variables that are differentiated, but they are also equated to the right hand side algebraically. And that's how we get to the D. Well, this is like the explanations how we get the A, why this is the D, and what is the S. Okay, a lot of equations. And before we get to the example, I tell you this outlook. What did I want to say in this outlook? Okay. If S is equal to 0, then DAE is strangeness free. And this will also define an index, because we can index, this will be the numbers of differentiations and eliminations to make, just call this EA as free. Okay, if S is 0, then the DAE is strangeness free. And if it's not, then one can do something about it. Then one can differentiate the system and do an elimination. Then this S will get smaller, so that it will become eventually 0, and the number of steps that are needed that defines the strangeness index then. But yes, no worries. Okay, and yes. And now I wanted to just show you an example what these equations look like in practice. What does it mean? And here we take our circuit example. that we had in the first lecture. And this goes like, here we have the C for the capacitor, x3 dot minus x2 is this right hand side. And then we had those two equations here. And well, the first thing that the theorem says is that all these quantities, they are independent, invariant under local equivalence transformations. But still one might want to do first a little transformation so that all these quantities are easier to compute. And that's what we're going to do. We do a state transformation. So this will be a state transformation. So that transformation, so that the system looks easier. First thing that we do is define x1 tilde as this, x3, x2. You see why? Because then here we will only have cx1 tilde as the right hand side. Then we also define the x2 tilde to be this. So here we will just have the x2 tilde. It will turn out, and the x3 we leave like it is. Okay, and then so this will be this rewrite of the equations, which is equivalent because out of this x1, x2, x3 we can go back to, of this tilde variables we can go back to the actual variables. Just check. And what we can do, well, rewrite the system. So here we will have cx1 dot tilde is 1 over r x2 tilde. Here this difference we have to replace accordingly, and this will give us x2 tilde minus x1 tilde minus u, and this stays as it was. And this will give us the E matrix. So this will be E matrix will look like C 0 0 0 0 0 0 0 0. And the A matrix will look like, first line we will have a 1 over R. We will have a 1 over R here, 0 0. Here we have a minus 1 and a 1 and a 0. And here we have 0 0 1. Okay, these are like the equivalent matrices. Okay, and then we have to define all these spaces. Like, we go kernel of E, co-range of E, co-kernel, and co-range of this thing. And that we can do. So T kernel of E is this matrix 0 0 1 1 1 0 0 1. Well, that you should see. That spans the kernel. Then we need T dash. To put it there. This should complete this matrix, and this will be the 1 0 0. Then we need the Z, which is the co-range of E, which is the kernel of EH. Since this is symmetric, this will be just the same here. This will be 0 0 1 0 0 1. Okay, and then we need that HAT. So we have to multiply this ZH with this matrix and the T from this side. And what we see is that it picks out this part here. So this will be 1 1 0 0. Okay. So ZH. I can do this one. 0 0 1 0 0 1. Here's this H matrix 1 over R 0 minus 1 1 0 0 0 1. And the T was this matrix 0 0 1 0 1. no. No. Well, I like C already. Like here's this identity block, here's this identity block. And if this multiplied to this will pick up this part here. Okay. Trust me. Otherwise, feel free to calculate that. Alright, this is that HAT. And then we can already define the A, which was the rank of the ZHAT, which is 2. Okay. And then we can compute the V, which was, what was the V again? The co-range of this, so the kernel of the transpose. But this will be, since this is full rank, this will be just a 0 vector. Co-range of ZHAT, and this will be just this vector 0, 0, like the kernel of the transpose of this. And yeah, this is just the 0, and then we can compute VH ZH AT dash, because this is what we need to define the strangeness. So this is this part. But yes, this is like 0, 0, then some matrices, and T dash was this one, right? Yeah, T dash is this one, and well, and since we multiply a 0, then this can only be the 0. So this is this, which means we also have that. So A is rank, this is 2, and the S was the rank of this part, VH ZH AT dash. And this is 0. So this doesn't have a rank. Or this it has a rank, but it's 0. Okay. Well, then we can still define what is the D. D was R minus S. What was the rank of the E matrix? Here the rank is 1. So it's 1 minus 0. So it is 1. Here's 1, S is 0, and the A is the 2. Okay, that's it. That's the lecture. Just checking when I forgot something. No, okay, that's the lecture, and well, in the script, have a look there. There I have shown this for the linearized. For the linearized Navier-Stokes equations. There's another example on this. Yeah. Okay. That's it for today, and well, see you for the next lecture. Bye bye.